All right, good morning. Welcome to Thursday morning lecture, last lecture before reading break. So we'll push through this, cover some good stuff, and then take a nice little break, get caught up on everything that needs to be caught up on. Okay, so start with our normal question. We're looking at one of our division properties. If A divides B and B divides C, then we have this intuition that A should divide C. We've used this a couple times. Why? Good, really good. So, when doing these divisibility proofs, we don't have too many things, especially these basic divisibility properties, we don't have too much to work from. So what does it mean for A to divide B? A divides B means that B is equal to A times n for some integer n. And B divides C means that C is equal to B times m for some integer m. So we want to prove A divides C. That means we want to show that C is A times some integer. Well, we have C is B times m, and B is AN times m. So this is A times the number n times m. Therefore, A divides C. So a nice little proof just from the definition of what it means for A to divide B, B to divide C. We get A to divide B, B to divide C, A divides C. By finding the thing we multiply A by in order to get C. Questions about that one? Not too complicated, but a good example of the types of proofs we might ask you to write. Okay. Next, I want to talk about the division algorithm. Okay, so this is a theorem. This says if A is an integer and B is a positive integer, then there exist unique Q and R, both integers, with 0 less than or equal to R, strictly less than B, such that A is equal to B times Q plus R. Okay. This is called the division algorithm. And when I write it this way, looks a little bit scary. All right, we got 4 variables running around, A, B, Q, R. But it's saying something really, really simple. The division algorithm says you can divide with remainder. So the colloquial way to say this is dividing. Just try that whole one again. Dividing with remainder is possible. So if A was, say, 10 and B was 4, I'm claiming that I can write 10 is a multiple of 4 with a remainder. Or in other words, 10 divided by 4 is 2 with a remainder of 2. And this unique part says 10 divided by 4 really is 2 remainder 2. It's not. One remainder 6. Right? It is true that 10 is equal to 1 times 4 plus 6. But we don't say the remainder is 6 because 6 isn't smaller than 4. Right? We can get another 4 out of there. We can get 2 full 4s with 2 leftovers. And it's also not 3 remainder negative 2. Because you can't get 3 full 4s and have negative 2 left over. We want our remainder to be positive, and we want our remainder to be smaller than the thing we're dividing by, so that we have as many copies of the thing we want as possible, and then whatever is left over. Okay, so this is the division algorithm. We're going to prove this. And this is the first time we're proving a statement about unique values, which is why I want to do this proof. So when proving something about there exists unique values, we're going to do it in 2 steps. So proof has 2 steps. Step 1 is to show that Q and R exist. And step 2 is, now we know that they exist, show that they're unique. So we're going to do those in 2 separate steps. Okay. So proof. We'll start with step 1. We want to show Q and R exist. The easiest way to show that something exists is to just find it. But we need to show that they always exist, so we're going to use induction. That's the takeaway here. So this is an important question. Let me pause here. What are we doing induction on? I got 4 different variables running around here. A, B, R, and Q. Which variable do I want to put in my statement? Which is the variable that's growing? So I don't want to do induction on Q and R. I don't want to do induction on R because R is stuck between 0 and B. There's only B different choices for R. So it's not going to be true for all the integers. Q is a better guess, but Q is not actually the thing that's controlling what's going on here. So good guesses, but not what I want to focus on. What's the number, the biggest number in the whole problem? A. Really good. I want to think about A. If I can prove this for all A, and then whatever B you give me, then I've proved the statement. But it's not immediately obvious how to do induction on A, because A is any integer. So we're going to let d of A be the statement that there exists Q and R both integers, 0 less than or equal to R less than B, such that A is equal to Q times B plus R. But I've mentioned B in here. B in this case is a free variable. It's not bound up by anything. So I should mention that this should be true for any B, or for a fixed B. So I'm fixing a B. I'm doing induction on A. This will be any positive B, maybe I'll even say, for a fixed positive B, let d of A be the statement. There exists Q and R in the integers. R is of the appropriate size, such that this statement is true. Now here's the thing about induction. I can't do induction negative. Right? The way induction works, you got to pick a starting place, and then, and your starting value could be negative, that's fine. But you pick a starting value, and then you go up. So how am I going to get all of my integers? I'm going to have to consider cases. Yeah, so why am I choosing A? I'm choosing A because A is the variable that can be any integer. A has the biggest range. I want to prove that this is true for any A, because A is the value that's equal to everything on the other side, right? I've got A equal to this stuff. I want to show I can put any number here. It's maybe not the best explanation, but that is the reason. Also because it's what works. But okay, so first I'm going to assume that A is greater than or equal to 0. Right? In order for me to do induction, I need a starting place. I'm going to start with A greater than or equal to 0. So my base cases, because I'm going to need strong induction for this, I'm going to do a separate base case for every different value of R that's possible. So D of 0 is true because A is equal to 0 times B plus 0. And D of 1 is true because A is equal to 0 times B plus 1. And I can keep doing base cases all the way up to D of B minus 1. Remember, B is a fixed number, and it's positive. So even though I'm omitting some of the steps here, why is this okay? Well, because I'm writing a proof. I'm claiming that this is rigorous, and you understand what goes into those ... dots. So we've effectively communicated what has to go there. I can't just do, and it's true for all cases this way, because it's not fair to ask your reader to do infinitely many cases, right? They would never be able to write them all down. But if I actually picked a B, if I said B is 112, you can write down 112 base cases. It'll take you a while, but that's fine. For any fixed b, this proof works. Which is why I'm allowed to say I have all of these different base cases. So now my induction hypothesis is going to be let k be my largest base case and assume d of 0 and d of 1 and all the way up to d of b minus 1. I want all of these as options. All right, and then how's my induction step actually going to work? I know that if I take k plus 1 and I subtract off b, well, I know b is a positive integer, which means that this is at most as big as k, but also greater than or equal to 0. This is why my base cases had to go as high as they did. I wanted to make sure when I subtract off b from my next case, I still get a positive number. I still get greater than or equal to 0, but I'm still smaller than k. The point is that this k plus 1 minus b is one of the things I assumed. It's in my induction hypothesis. So d of k plus 1 minus b by induction hypothesis. This means that k plus 1 minus b is equal to some q1 times b plus r1. So what am I doing? I'm saying I want to write k plus 1 in this form, q times b plus r. I don't know how to do that yet, but I do know how to write k plus 1 minus b in this form, q1b plus r1. Okay. And now I can move, with 0 less than or equal to r1 less than b, because that's what my induction hypothesis says. And now I just want to move this b over to the other side. q1b plus b plus r1, which means that k plus 1 is equal to q1 plus 1 times b plus r1. And I still have this condition that I need. I needed r1 to be stuck between 0 and b, and it is. I get the same remainder. So what am I really doing in this induction step? I'm really saying, okay, why can I divide k plus 1 by b? Well, I take off 1b, and what I have left is covered by my induction hypothesis. And then dividing k plus 1 by b is just one more copy of b than if I subtracted off of b. Okay, but remember, all of this, so let me finish this. Therefore, d of 0 and d of 1 and all the way up to d of k implies d of k plus 1. So d of a holds for all a greater than or equal to 0 by strong mathematical induction. But I'm not done. I'm not done with my proof. If I go back here, I'm not done with my proof because that was just step 1. But I'm not even done with step 1 because this only handles a greater than or equal to 0, but a is supposed to be any integer. So that handles the a greater than or equal to 0 case. I also need to handle a is less than 0. So now assume a is less than 0. I got to do a separate case. Again, common theme throughout the course. I'm a mathematician, I'm lazy. I don't want to do a less than 0 again. I don't want to do another induction for sure, if I can avoid it. So I want to use what I've already done. I want to reuse my work. If a is less than 0, then negative a is greater than 0. I've already handled cases that are greater than or equal to 0. So by previous case, I know that negative a can be written in the form b times q plus r with 0 less than or equal to r less than b. Okay. Now, I want to solve this for a. That means that a is equal to, I'm going to multiply the minus sign on the other side and distribute, b times negative q minus r. So b times minus q, that's fine. That's not a problem. Q is allowed to be negative. But I'm not quite done yet here because minus r is not in the right range. R is between 0 and b, but minus r has to be positive. Not quite done. Need 0 less than or equal to r less than b. But right now I have a negative r. So I'm going to do one more trick. I'm going to add an r. I'm going to add a copy of b and then subtract it back off. A is going to be equal to b times minus q minus b plus b minus r. Why am I doing that? Well, this is just another copy of b. So this is b times minus q minus 1. And this, b minus r, is going to be, because r was stuck between 0 and b, b minus r is also going to be stuck between 0 and b. Note that 0 is less than b minus r is less than or equal to b. So I was a little bit sloppy here. If r was equal to 0, then we actually are done. So not quite done unless b equals 0, or unless r equals 0. If r was equal to 0, then we're all good here. A is equal to b times negative q plus 0. 0 is in the right range. But if r was not 0, then negative r is a negative number. That's not allowed. So what do I have to do? I have to do b minus r, in which case I am strictly less than b. Okay. I'm going to pause here. This is a long proof. The proof of the division algorithm, it's the longest proof we've seen so far in the course. Where are we? We have these two steps. We haven't gotten to step 2 yet. Right now, we're just showing that Q and R exist. For A greater than or equal to 0, we did an induction. We covered that case. And now, we've shown if A is less than 0, we can use that same induction to cover the A less than 0 case. So we've completely proven step 1. We've shown that these Q and R do exist. You can really find a Q and an R such that R is stuck between 0 and B. A is equal to Q times B plus R. The last thing we need to prove is that they're unique. Lastly, Q and R are unique. So, this is important. This will come up again. How do we prove that something is unique? Well, the basic technique is going to be to pick 2 ways of writing it. Let Q1, R1, Q2, R2 with 0 less than or equal to R1, R2 less than B satisfy Q1B plus R1 is equal to A, which is equal to Q2B plus R2. What I'm saying is take two solutions. I know Q and R exist, so I know there's at least one way to do this. But take 2 ways to do it. My goal is to show that Q1 was Q2 and R1 was R2 all along. My goal is to say, pick 2 ways to solve the problem. Hey, look, you actually only chose one way. You tried to come up with 2 different answers, but you actually came up with the same answer twice because there is only one answer, because the answer is unique. So this is how we show uniqueness. Okay. So, because these 2 things are equal, 0 is equal to A minus A. Right? That's a nice, easy statement. And I'm going to write A in these 2 different ways. One way of writing A was Q1B plus R1. And my other way of writing A is Q2B plus R2. And if I rearrange this, I get Q1 minus Q2 times B plus R1 minus R2. Okay. So if Q1 is equal to Q2, if Q1 is equal to Q2, then this says 0 is equal to 0 times B plus R1 minus R2. And if I add R2 to the other side, I get R2 is equal to R1. And that's what I want to show. Q1 is equal to Q2, R2 is equal to R1. I've met my goal. So the answer is unique. But what if Q1 is not equal to Q2? Well, if Q1 is not equal to Q2, then I can divide by it. This is a trick. If two things are not equal, then you're allowed to divide by their difference. Right? In this case, I can't divide by Q1 minus Q2 because they're equal, and you're not allowed to divide by 0. But if they're not equal, then I'm allowed to divide. So if Q1 is not equal to Q2, then I can divide by Q1 minus Q2. And if I divide both sides by Q1 minus Q2, I get 0 divided by Q1 minus Q2 is still 0, is equal to B plus R1 minus R2 divided by Q1 minus Q2. And here I have a problem. My problem is that B is supposed to be an integer. So maybe let me subtract this to the other side. Or negative B is equal to R1 minus R2 divided by Q1 minus Q2. So what I get on this side is supposed to be an integer. But I know that these two values are both less than B. They're stuck between 0 and B. So I know, is this what I wanted to write? Sorry, that's not what I wanted to write. This is true, but it's not going where I want to go with it. I want to just rearrange that slightly. 0 is equal to B plus R1 minus R2 over sorry. Yeah. It's not Q1 minus Q2 I want to divide by, it's B that I want to divide by. That's why I'm getting confused. Q1 not equal to Q2, then I can divide by B. And when I divide by B, this will work out better. I get 0 is equal to Q1 minus Q2 plus R1 minus R2 divided by B. And I can move this over to the other side. Q2 minus Q1 is equal to R1 minus R2 divided by B. And this is where I'm going to find my problem, right? I want this to not be a case that's possible, which means I want to come up with a contradiction somehow. My contradiction is going to be this side is an integer, and this side can't be an integer. This side can't be an integer because R1 and R2, all the way back up here, were both smaller than B. So R1 minus R2, I can't get all the way up to B. R1 minus R2 is stuck between B and negative B. Right, the biggest this could possibly be, R1 could be B minus 1, R2 could be 0. But then I still don't get all the way up to B. And the smallest this could possibly be is R2 could be B and R1 could be 0. So I could get down to negative B minus 1, but I can't get all the way down to negative B. So this side is an integer. And this side is not an integer. Which means I have a contradiction. Which means this q1 not equals 2 case was not possible. Oops. Not possible. Okay. So I have shown my goal. The only case that's possible is q1 is equal to q2, and when q1 is equal to q2, r1 also has to be equal to r2. So finally, therefore, q and r exist and are unique. Whole proof. Ready? Started with this statement. Proved it for a greater than or equal to 0 by induction. Strong induction. Needed a whole lot of base cases. Did our proof by strong induction. That was good for the positive A's. Negative A's had to be separate, but we could reuse our work. Reused our work successfully. Now we know Q and R always exist. We just need to prove that they're unique. So we picked two different answers and showed that if Q1 was equal to Q2, then we actually only picked one answer. We picked the same numbers twice. And if Q1 was not equal to Q2, well, you got a contradiction. Because you have an integer that's equal to a non-integer, and that can't happen. Whole proof. I even tried to write it out ahead of time. And still a couple slight mistakes. So, you know, proofs take some writing and revising. It's like an English essay. This is a second draft of the proof. Maybe if I wrote it a third time, I would change something else. I would make it slightly different. But it's an argument. It's a discussion. I am justifying to you that this works. Okay, let me pause there for questions. How are we feeling? Okay, that was a lot. Let's take our break. 2 quick minutes. Go grab a snack, stretch, run to the restroom, whatever you got to do. We'll come back 10 minutes past the hour. We'll keep going. A couple of people just left the meeting. And I like to think that they were like, proof was just too much. I'm done for the day. Can't handle anything else. Which is a shame, because now we're going to get to the good part. Today's theorem is horrible. No, the theorem is nice. The proof is horrible. Important to separate the two. Okay. We're back. Okay, so we spent the first 35-ish minutes of the class on this proof. What did I even prove again? Why did we spend so much time on this? All I did was prove we can divide. Great. Okay, JD, yeah, I know. I did division in grade, 2. Speedrun it. Maybe not grade 2. Grade, 3 or 4 at least, though, you were dividing. Why are we worried about dividing? Well, this proof is what makes your computer work. So if you like your computer, thank the division algorithm. What am I talking about? Our next topic are alternate bases. The division algorithm says I can divide things with remainder, and that turns out to be super important. If I look at the number 29, and I divide it by 16, 29 is 1 times 16 with a remainder of 13. And then if I look at 13, 13 divided by 8 is 1 with a remainder of 5. And if I look at 5, 5 is 1 times 4 with a remainder of 1. And if I look at 1, it's 0 times 2 with a remainder of 1. And if I look at 1, it's 1 times 1 with a remainder of 0. All of this I've done with the division algorithm. But what it means is that 29 is equal to 16 plus 8 plus 4 plus 1. Or, in other words, it's equal to 1 times 2 to the 4th power plus 1 times 2 cubed plus 1 times 2 squared plus 0 times 2 to the 1st power plus 1 times 2 to the 0th power. Or, if I just record all of these digits, 1, 1, 1, 0, 1, in base 2. This was an introduction, but let me actually talk about what I mean now. If D1, D2, all the way up to dk satisfy 0 is less than or equal to d sub I is less than q, we write dk, dk minus 1, d2, d1, base q to mean the number dk times q to the k. I guess I really want a d0. A d0, d1, all the way up to, so just cheat a little bit, change that all the way down to d1, d0 to mean dk times q to the k plus dk minus 1 times q to the k minus 1 plus all the way down to d1 times q plus d0. So the number 11101 base 2 means 1 times 2 to the 4 plus 1 times 2 cubed plus 1 times 2 squared plus 0 times 2 plus 1 times 2 to the 0. Let me do some more examples quickly. $29 is equal to 1 times 27 plus 2. 2 is equal to 0 times 9 plus 2. 2 is equal to 0 times 3 plus 2. And 2 is equal to 2 times 1 plus 0. Which means 29 is equal to 1 times 3 cubed plus 0 times 3 squared plus 0 times 3 plus 2 times 3 to the 0, or 1002 base 3. What is the statement at the end? The statement is these digits, parentheses with a Q, means this sum. Which I ran out of room, so I wrote the plus D0 in the next line. I can also write 29 is equal to 1 times 16 plus 13. And then 13 is equal to 3 times 4 plus 1. And 1 is equal to 1 times 1 plus 0. So 29 is equal to 1 times 4 squared plus 3 times 4 plus 1 times 4 to the 0, or 131 base 4. So the idea of alternate bases is that I can write my number using only the digits 0, 1, 2, all the way up until q minus 1. And the division algorithm says that we could always do this. For any base that you want to use, I can write a number just using those digits. By the way, this also works for base 10. 29 is equal to 2 times 10 plus 9. And 9 is equal to 9 times 1 plus 0. So 29 is equal to 2 times 10 plus 9 times 10 to the 0, or 2 9 base 10. That's why we write 29. This means 2 in the tens place means 2 tens. But if we're in base 4, a 1 in this position, this is not the hundreds position. This is the 16s position, because 16 is 4 squared. I have a 1 in the 16s position, I have a 3 in the 4s position, and I have a 1 in the 1s position. Here I have a 1 in the 27s place, and then a 0 in the 9s place, a 0 in the 3s place, and a 2 in the 1s place. So you can also go the other way around. If I write down something like 1, 3, 4, base 5, I can figure out what this number is in base 10 by saying this is a 1 in the 5 squared place, a 3 in the 5 to the 1 place, and 4 in the 5 to the 0 place, which gives me 25 plus 15 plus 4 is 44. Okay, so a couple bases that we use frequently. We don't often use base 5. It's just not a number that's super helpful a lot of the time. But we do use binary. Yes, this is how we convert between bases. So binary is a special name for base 2. Basically, everything in your computer uses binary. So base 2, very important. Sometimes when talking about binary things, we use octal. This comes up a lot in colors. Octal means base 8. The name of base 10 is decimal. The decimal point is because you are in base 10. It's the octal point if you're working in base 8. And then hexadecimal also comes up a lot in computing because binary strings are very long. If you have a 64-bit computer, that means your memory address has 64 ones or zeros representing a binary number. And nobody wants to write out 64 ones and zeros. So they use hexadecimal instead because it's shorter. This is base 16. Except there is a problem with base 16. Let's write 29 in base 16. 29 is 1 times 16 plus 13. And 13 is 13 times 1 plus 0. So how do I write 29 in base 16? First digit is 1, but the second digit is 13, but I don't have a digit, I don't have a symbol that means 13 because we use decimal to talk about numbers. We don't have one symbol that means 13. 13's too big to fit into a single symbol in decimal. So we need more symbols. And I think it would have been cool if we had just come up with brand new symbols, but we didn't. We just used letters. So A means 10, B means 11, C means 12, D means 13, E means 14, and F means 15. So if we wanted to write 29 in hexadecimal, it would be 1D. 1 in the 16's place, D in the 1's place, D meaning 13. Sometimes computer scientists like to write OX in front of their hexadecimal numbers. So you might see something like OXFFFF. And this means 15 times 16 cubed plus 15 times 16 squared plus 15 times 16 plus 15. Which in binary works out nicely as 1111, 1111, 1111, 1111. Or 2 to the 32 minus 1, whatever that number comes out to be. Okay. What's the best part about learning alternate bases? I get to make some really terrible math jokes. This is going to be everybody's least favorite lecture. We've just done a big long proof. Time for some terrible math jokes. Ready? They say that there are 10 types of people in the world. those who understand binary and those who don't. No, this is important. This will be on the test. This won't be on the test. You know, they say that there are 10 types of people in the world. There are those who know hexadecimal. And F the rest. This one, there are 10 types of people, but 10 is 2 in binary. 1 times 2 to the 1. Those who know binary and those who don't. This one's kind of an old-fashioned joke. This one I like a little bit better. 10 types of people. That's 16 types of people. Those who know hex are one of them. That leaves 15 types of people, but 15 is F in hexadecimal. So there are 10 types of people, those who know hex, and F the rest. Why did the computer scientist dress up as Santa for Halloween? Why did the computer scientist dress up as Santa for Halloween? Well, you see, he got confused. Because 31st of October is 25 of December. Because 31 in octal is 3 times 8 plus 1 is 25 in decimal. These jokes are really bad, and they're even worse somehow remotely. Because, like, at least in a classroom, there would be like 90 of you just all groaning of like, these are terrible. But I'm just saying this to an empty room. Like, my neighbor is getting ready for work and is listening to these terrible jokes. They're falling even flatter than they would in a room full of people. These are the sacrifices I make for you. I just have to imagine all of you groaning. Yeah, my neighbors totally think I'm crazy. They just hear me talking to myself every Tuesday and Thursday morning. Just pretending. Role-playing as a math teacher. Okay. One more thing I have to say about alternate bases. Alternate base questions, change of base questions, are really easy to write. And math professors are really lazy. Just a good thing to keep in mind, you know, come quiz time. Anyway, let's move on. Next topic, common divisors. Back to math. See, if I tell you enough terrible jokes, you'll be like, please, just do more math. I can't take any more of the jokes. If A and B are in integers, then C greater than 0 is a common divisor of A and B. Ugh. Common divisor of A and B if C divides A and C divides B. So let's look at 24 and 36. So what are the divisors of 24? What are the positive divisors of 24? We've got 1, 2, 3, 4, 4 times 6, 3 times 8, 2 times 12, 1 times 24. For 36, 1, 2, 3, 4, and 6. 6 times 6, 4 times 9, 3 times 12, 2 times 18, and 1 times 36. So the common divisors of 24 and 36 are 1, 2, 3, 4, 6, and 12. Those are all common divisors of 24 and 36. And the greatest common divisor which we write, so of A and B, which we write GCD for greatest common divisor of A and B, is the common divisor that satisfies two conditions. First of all, it has to be a common divisor. So C is a common divisor of A and B. And 2, if D is any other common divisor, then C is at least as big. This is just a fancy, this is our formal way of saying C is the biggest one. Okay, so what is the GCD of 24 and 36? What is the biggest number that divides both 24 and 36? Yeah, good. If we look at our list of divisors for each, we've listed out all the divisors, we circled all the common ones. The biggest thing that divides both of them is 12. So it's not 1 times 2 times 3 times 4 times 6 times 12. That won't actually divide them. So we're not looking at least common multiple, which I think is what you were thinking of, but wouldn't be that either. But greatest common divisor. The greatest common divisor here is 12. This is the biggest number on my list that divides both of them. So a couple quick examples. What is the GCD of A with itself? Tricked you. Very close. Absolute value of A. So, got to pay very close attention to our definition. A and B can be any integers, but the greatest common divisor has to be positive. It has to be strictly greater than 0. So the GCD of A in itself is absolute value of A, just in case A is negative. What is the greatest common divisor of A with 0? Not sure. We got a 0. Well, the answer can't be 0 because 0 is not a common divisor. Have to pick a number bigger than 0. Greatest common divisor of a and 0, absolute value of a again. Because here's the question, what is a divider of 0? Any number is a divider of 0, right? Because x divides 0 for any x. 0 is equal to 0 times x. So the greatest common divisor of a and 0 is just the biggest thing that divides a. 0 is not a problem. One last question. What is the greatest common divisor of 0 and 0? Still can't be 0. GCD can never be 0 because divisors can't be 0. Have to pick a number greater than 0. Yeah, here we have a problem. This one is undefined. We don't define the GCD in the case that both numbers are 0, because any number you plug in works. Any number is a divider of both of them. So there is no biggest one. So GCD 0, 0 doesn't exist, but GCD A, 0 exists just fine. I guess we could also say GCD of A and 1. This is another easy one. It's the biggest number that divides both A and 1. Just 1. Good. Okay. So here's the thing about GCDs, though. We don't want to have to write out the factors every time. That's going to be a huge pain. So imagine I wanted to know the GCD of 510 and 108. I don't want to have to factor these numbers, let alone bigger numbers. So I need a new strategy. That new strategy relies on this lemma. A lemma is like a theorem, but it's just a little smaller, littler. Lemma, little theorem. And that is, for every integer, the GCD of A and B is equal to the GCD of B and A minus B times X. So this is proved in the theorems and theorems and definitions document. I don't have time to prove it right now, but it's a nice little proof. It's very similar to what we did with uniqueness. You let C be this GCD, and you let D be this GCD, and you're going to end up showing that C is less than or equal to D, but D is also less than or equal to C, which means that they're equal. Which is a nice little way to prove something. But you'll have to read about it in the notes, because I want to talk about the Euclidean algorithm. So the Euclidean algorithm is how we find GCDs. And here's how it works. Using that lemma, sorry, 510 and 108. So my first step is to write 510 as a multiple of 108 with a remainder. So I'm using my division algorithm. So 510, I need to divide by 108 with remainder. I can get 4 copies of 108 in there. That gives me 432 with a remainder of 78. That's step 1. And then everything shifts over a step. So now I'm going to write 108 as a multiple of 78 with a remainder. Well, I can only fit 1 copy of 78 in there with a remainder of 30. And now everything shifts over again. So now I'm going to write 78 as a multiple of 30 plus a remainder. And in this case, I can fit in 2 copies of 30 with a remainder of 18. Everything shifts over again. This is the algorithm. We just keep repeating this. 30 as a multiple of 18 with a remainder. In this case, 1 times 18 plus 12. Write 18 as a multiple of 12 with a remainder. And last but not least, ran out of room, I write 12 as a multiple of 6 with a remainder. When I get to this 0, I know I'm done. And the GCD is the last thing that shifted over. This is the GCD. GCD of 510 and 108 comes out to be 6. Because what am I secretly doing here? What I'm writing is the GCD of 510 and 108 is equal to, well, I use my lemma. It's equal to the GCD of 108 and 78. Because I'm doing, my lemma says I can take B and then I can take A minus 4 times B. And if we take a peek back at my lemma, this is the same as the GCD of 108 and 510 minus 4 times 108, which happens to be 78. And that's equal to the GCD of 78 and 108 minus 78. And that's equal to the GCD of 30 and 78 minus 2 times 30. So I'm going all the way down until my very last step is equal to the GCD of 6 and 12 minus 2 times 6. But this is just saying the GCD of 6 and 0, which we know is 6. And so we can follow this path all the way back up to the GCD of our original 2 numbers, 510 and 108. So this is the Euclidean algorithm. Where did this 4 come from? This comes from the division algorithm. How many times does 108 go into 510? 4 with a remainder of 78. 4 is the largest number of 108s I can fit in. So this is the algorithm. This is what you need to practice over and over again. 510, 108, do the division algorithm to get your Q and your R, and then shift over and do it again, and shift over and do it again, and shift over and shift over until you get down to a 0. The last thing that you shifted over is your GCD. Okay, we'll talk a little bit more about this after reading week, but I will stop there. I have office hours today if there's anything you want to chat about. Otherwise, yeah, have a good reading week. Good luck getting caught up on everything. And yeah, I'll see you hopefully with some warmer weather on the other side.